Hello, everyone. Thank you for joining today's Slang virtual meetup. We have an exciting hands-on session today that will walk us through creating a Gaussian splat using Slang. Our speaker today is the chair of the Slang Working Group, Shannon Woods, Principal Graphics Technical Program Manager at NVIDIA.
Hello, everybody, and thank you for joining me for the first Slang community virtual meetup. So today I plan to start with the very basics of how to download, install, and set up Slang, and work through an example with you all the way up through creating your first Gaussian splat. So many folks in attendance may already be familiar with Slang, but to give a very, very quick overview for anyone else, Slang is both a shading language and a compiler that ingests that shading language and outputs to a number of different formats for use across different APIs and platforms. For folks familiar with HLSL, you'll notice that Slang's syntax is very similar, although it adds a number of modern language concepts like generics and interfaces, which I'm going to touch on in my example. Slang also provides a powerful automatic differentiation system, and that's a first among GPU-targeted languages. This is the technology that empowers us to work with neural graphics techniques like Gaussian splatting more easily. So this session is going to build towards that end. So with that, I'm going to turn off my video and share my screen so you can see what I am doing. All right. Okay, cool. My screen should be visible now. Awesome. All right, so let's get started with getting Slang installed. What you're going to need is going to vary depending on how you intend to use Slang. If you're exploring the machine learning side of the world using Python, setup is extremely simple. Now, as prerequisites, you'll need Python 3 and the Python package manager pip already installed. Also, if you're on Mac OS, you're going to want to have installed Xcode because that's what provides the support for Metal underneath of Slang. So installation is straightforward. All you need to do is pip install SlangPy, and you're going to see I've already got it installed. If you didn't, pip would take care of installing all of the dependencies for Slang for you. And we can quickly verify that it installed successfully just by opening up our Python interpreter and doing an import of SlangPy. And I get a warning about the D3D12 Agility SDK. This is just because I don't have my path set correctly. It's not going to affect anything. I can still use the D3D driver just fine. So I'm going to verify that I have my correct SlangPy installed by printing the SlangPy version. It's version 27. That is up to date. So I know it is installed correctly. Awesome. So if what you want to do is invoke Slang kernels from your Python code, that's all you need to do to get set up. It's that simple. But if you're looking to compile Slang either from the command line or at runtime using a C or C++ API, which is a pretty common use case for graphics developers, then you need to do a little bit more setup. So what I'm going to do here is just go to the Slang GitHub and navigate to our releases page. You're going to want to take whatever the latest release is. There will be lots of build assets here. You're going to want to choose the correct one for your platform. For me, this would be Windows x86 64, but nobody wants to watch me download stuff. So I already have it downloaded and extracted here. If you're going to compile from the command line, all you're going to need to do is use the slang C binary from the bin directory. You're going to want to stick these somewhere that makes sense for your system. I have actually stuck them just in this Slang libs directory here, which is not the best choice for if I'm going to be using it for a number of different projects, but I just wanted to get set up for this demo here. So if you're compiling at runtime, the pieces that you're going to want to use uh, from those libraries, I've got just the binary include and lib directory. There's a slang.h file in include. The slang C binary is in bin, and also in bin is the slang DLL that I'll use here on Windows. If you're on Linux, it'll be libslang.so, and on Mac OS, it'll be libslang.dilib. And you're going to want to make sure that the Slang library directories, where that DLL or what have you sits, is available not just in your library search path in your compiler, but also in the runtime path, so it can be found at runtime. You can also optionally, but I highly recommend it, install the Slang language server extension for Visual Studio or Visual Studio Code or any other IDE that supports it. I believe there are a couple. And this is going to provide all of that IntelliSense goodness that you might be used to. So looking over here at Visual Studio, you can see I've got my syntax highlighting. I can mouse over things and see all of the information about their type defs and whatnot. So this here is we're going to look at a really minimal example of runtime compilation. Now I've published this code online on my own GitHub. If you'd like to browse it, we'll drop the link in the chat. But it's very bare bones. This is just the very minimum code that you're going to need to compile a module in Slang. So taking a look here at the C++ side of things, what I end up doing is first I create a global session, which this is just the call that instantiates the compiler and its API, which gives it time to load any of the downstream libraries or tools that it needs on this platforms. Most projects are only going to do this once during execution. You're going to have one global session that is just, this is how I access the Slang compiler. But then we have to set up a local session, which you can think of as similar to a context for running the Slang compiler. This will package up all of the information that you need to provide about compiler flags, library paths, if you're providing information about the entry point or the compiler stage, or what profile you're compiling with, that will all be set up in your session description. So there are a ton of options that you can use in your session description. I touched on a bunch of them. This is also where you'll stick preprocessor macros, lots more. So in the code here, I've stuck a link to the documentation for the compilation API. So you can browse that at your leisure and see the dizzying array of options. But I am going to keep things really simple for the moment and leave everything at the default. I'm going to set a compile target. This part's important because otherwise Slang does not know what you want to compile to. I'm going to say I would like to get SPIR-V out of Slang, and I specifically want SPIR-V 1.5. So I set up the target description to have SPIR-V as the format and SPIR-V 1.5 as the profile. I'm not going to provide any other compilation flags or targets. You can compile to multiple targets with a single call, but I'm just going to leave things as a single compilation to SPIR-V 1.5. So now that I have that description created, I can actually create this session, and this will be how I kick off any compilation with those specific options to Slang. So now that we have our compiler session, the next thing to do is retrieve the Slang module. This loads it from the file, but doesn't perform linking or compilation yet. This just uses the load module function, which is one of the functions provided by the session. You're going to provide it both the name of the file. Here I've just provided myshader.slang, which is this guy over here. I have it in the same directory that I'm going to run from, so I don't need to provide it any other path information. And then you also give it a pointer to just a blob where it can stick any diagnostic information. If anything goes wrong with compile, you'll get information about it in this diagnostic blob. But I'm going to play fast and loose and not actually check the diagnostic blob. I'm just going to check to make sure that we got a valid pointer out of this load module call and print an error message if I don't. So now that we have loaded the file correctly, the next step is linking our shader program. Now I am just using a single module for my compute shader. If we had multiple stages to chain together, or our code was spread across multiple modules, we would need to load each of them, identify the entry points, and compose those modules into a single composite for linking. That's documented on the compilation API page that's linked farther up in the code. But I am just using one single module right here, so I can just immediately advance to linking. And similar to loading, link is just a call on the module that can create diagnostic blobs if anything goes wrong. You provided a pointer to return that information to you. And this one will also generate a Slang result to give you a simple answer about whether the linking was successful. So I print an error message if it wasn't, and continue on to the actual compile. So from our linked program, we'll be able to call get target code, and this is going to use the information that we already provided about our target and profile in the session description to kick off that compilation and give us a pointer to a binary blob of compiled code. So I'm not actually going to do anything with my compiled code because that would require setting up a Vulkan context to deal with all of that. I just want to compile it. So I'm going to print myself a happy message and pat myself on the back once the compilation is successful. One other note that I've included here is that I'm being really terrible and not cleaning up after any of these allocations. So if you use this in your own code, you're going to want to be much tidier. But we just want to demonstrate, okay, we can compile this thing. All right, so I compiled my my compiling, and I am currently grayed out for some reason. Maybe. All right. Well, normally I would be running this for you, but I don't know why I am currently unable to run. Perhaps I've got something set up weird about my environment. But we can turn to the command line API, which is the next thing I was going to show you anyway, to compile the same code from our command line. So what I'm going to do here is go into my Slang basics directory, and this is the minimal Slang compilation example. This is the same code over here that I have open in Visual Studio, but now I'm going to just invoke the command line compiler to compile to my desired target. Now, because I left Slang C up in that Slang libs directory, I'm going to have to directly reference it from there. I haven't got set in my path, but you can add it to your path if you would like to do less typing. Cool. So I can invoke my Slang compiler from the command line on, let's see, I've got my shader.slang. Cool. And I have to give it some information about how I want to compile, what I want to compile to. But the command line compiler is pretty clever about figuring out what it is you wanted to do. So if I just tell it I want to send the output to an output.spearv, it'll automatically detect, okay, spearv is what you want to compile to. And it takes a second. All right, all done. And I can use Notepad to open up my glorious SpearV file, and you can see, hooray, I have just a bunch of SpearV, which is mostly unreadable because it's binary. Awesome. If we wanted to see something that's a little bit more legible, we could target HLSL. And once again, because of the file extension, Slang is going to be able to automatically detect that we want HLSL. But one thing about targeting HLSL is it also is going to need information about the entry point. So I can just provide it the entry point name here also as a command line option. So, all right. And open up my HLSL file. Hooray, I have some much more legible HLSL. That is the HLSL equivalent of my shader. You can also try to be tricky, of course, and if you want to provide target information explicitly, and say, okay, I want spearv, but I'm going to give you a file name, output.hlsl. The actual explicitly provided target is going to be the thing that wins. So, oh, I didn't actually give it the file name, or I did give it the file name, but I forgot to tell it it was -o, the file name. So if I output to my HLSL now, oh, I've output spearv. And you just saw a second ago that if I omit the file name entirely, it will spill the spearv directly to the command line. It'll spill, your HLSL if you're targeting HLSL. Similarly, if you want to just take a look at what it looks like. What did I do? Target HLSL. Yeah. So you can see all of the possible options to the command line with slangc.help, which you want to just a -- help. This is really, really long. So I actually recommend taking a look at the online documentation rather than trying to get it from the command line. We have a bug file to make this a little bit easier to navigate. But I think we can drop a link into the chat that just goes directly to the command line reference with all of the different command line options. So you can browse them at your leisure. So that's compilation from the command line. If you want to do the whole kit and caboodle and compile Slang from source, you'll want to file the instructions on GitHub for building Slang from source. Your setup is going to vary a bit depending on your platform, but in general, you're going to need CMake and Ninja or another CMake compatible backend, a C++ compiler of your choice, and Python 3. On Windows, I tend to prefer Visual Studio. On macOS, whether you use Xcode for compilation or not, you're going to need it, the Xcode download, just because that's where the Metal support libraries are. So one other thing to mention before I move on from showing compilation examples is that Slang provides seamless integration with most existing HLSL and GLSL code. So I can quickly show you how to compile existing shaders using Slang. So looking in my directory, I can see I've got a vertex shader, a GLSL vertex shader here, sample shader.vert. If we want to take a look at that, I think I have it in my recents. Yes. So this is like a dead simple GLSL vertex shader. Now to compile GLSL in particular, this doesn't apply to HLSL, but to compile a GLSL on the command line, you're going to need to alert the Slang compiler that we want to operate in GLSL compatibility mode. So I mentioned earlier that Slang syntax is very similar to HLSL. So most of the time, if you pass HLSL into Slang, it doesn't hiccup, it just can read it as though it is Slang, and it doesn't need to have any additional options to let it know that this is HLSL instead. But for GLSL, syntax can be a fair bit different. So the command line compiler is able to pick up on the fact that you're compiling GLSL if the file suffix is .vert or .frag, much like it can understand your target based on file suffix. Also, if your file begins with a hashtag version, 450 or 150 or whatever, the compiler will assume it is GLSL because those directives only appear at the beginning of GLSL files. You can also use the import GLSL command at the head of the file. That's a Slang keyword that just imports a Slang module called GLSL that provides all of the standard GLSL types and such like. But there are some bits of GLSL syntax that don't work seamlessly if you've just done that import line or let it auto detect. So if you want to use some of the weirder corners of the syntax, like interface blocks, you're going to need to set a flag to enable GLSL. There is one for the online or the runtime compilation API. Is called enable GLSL, and it's set on the global session description. And then here on the command line, all you're going to need to do is, so if I Slang C, allow GLSL is the command line flag to let it know that you're going to be operating in GLSL compatibility mode. So I can do this and provide it my sample shader.vert and tell it I would like to target sphere V. And once again, it can just automatically figure out what the GLSL means and spit out some sphere V. And you can direct this to a target file or target HLSL or any of the other platforms, just like you could if you were compiling something else. So Slang is a full-featured compiler ready for use in a number of different kind of projects, whether you need to do offline or runtime compilation, and whether you need to hook into an existing C++ or Python project. So for the remainder of this session, I'm going to use the Slang Pi interfaces, in part because that allows me to skip a lot of the setup that I might otherwise need to do of the underlying graphics API. One note about that, one of the reasons that Slang supports a large number of target languages is so that you can write a shader that can be used across several different platforms and APIs. You write it once and use it in a bunch of different places. So you can take the same Slang shader, compile it to sphere-V for use with Vulkan, HLSL for use with D3D, or Metal shading language for use with Metal. I'm not going to go through the specifics of interacting with the platform-specific APIs here, as that's a really big subject in and of itself. But if you are new to shader and graphics programming in general, I or someone on our Discord can point you at some resources to learn more about that. And there will be a QR code that I'm going to put up towards the end of my talk that gives you the link to join our Discord. All right, so we've compiled a little bit of pre-existing HLSL and GLSL, but what we're really here for is to write some shaders in Slang, right? All right, let's get started with a simple compute shader. And for this, I'm going to bring up, I have a, somewhere back here, actually, I have my, there we go. This is Visual Studio Code. I just have this open because it's easier for me to have both Python and Slang correctly interpreted here. I have it set up better. Looking at our compute shading example, we're going to get started here. I want to take a look at our compute shader. So I didn't want to just write some slang that does exactly what the equivalent HLSL shader would do. So this example demonstrates a couple of Slang's key features that work together, generics and interfaces. So these are going to help us write flexible, reusable shader code that can work with different types and behaviors. So first, taking a look at the interfaces up here at the top. An interface is like a contract that defines what operations a type has to support. So in our example, we have this interface, I operation. Now, this interface says that any type that implements the I operation interface must provide a process method. And that process method has to take an input and return a result of the same type. It also uses one of the interfaces from Slang's standard module in order to constrain the type. So this interface can only be used with types that conform to the I arithmetic interface. And what that does is just require that arithmetic operations have to be defined for that type. You can find a reference to the interfaces available in the Slang standard module at our documentation, and we can drop a link for that in the chat as well. Now, interfaces like this work hand in hand with generics. Generics allow us to write code that works with any type rather than being locked to a specific one, much like templates if you're used to C++ or HLSL. So this T in our interface here is a type parameter. And it means that we can use this interface with integers, floats, or any other type, including user-defined types, as long as they satisfy this I arithmetic interface requirement. So we're going to create multiple generic implementations of I operation, which will work with any arithmetic type. And that's what we've done here with multiply by 2 and add. So one thing to note here in multiply by 2 is you'll see I'm casting this literal 2 value to type T. And that's because the multiplication operator for an I arithmetic has to be defined for both operands to be the same type. So because input is type T, I'm casting my numeric literal to also be type T. Now, you can see how much flexibility this generic style permits by combining these concepts down here in my buffer processor. So in the signature of buffer processor, we specify that it takes two parameters of type T and T operation, and T is required to conform to the I arithmetic interface, while the T operation is required to conform to the I operation of T interface. Those interface constraints are how we ensure that the operation is compatible with our data type. One of the cool things about this is you can see I've got this sneaky div operation defined up here. Now, currently, sneaky div conforms to the I operation interface, but if I were to take away that guarantee, say, no, this is just my sneaky div that I have defined, it's not an I operation, it's its own thing, but it still has T process T as a function signature. You can still call process, it should still work, right? Well, if I try to instantiate a buffer processor of this sneaky div operation type, or that conforms to this sneaky div operation type, I will get a complaint from Visual Studio. It's going to say, oh no, your sneaky div does not conform to the required interface. So this will kind of hold you to the type constraints that you intended, which can be super convenient, especially if you're working with a really large code base where you might not be the person who wrote that interface requirement. And so this can help you avoid shooting yourself in the foot and having to dig through compiler errors that contain lots and lots of angle brackets like you might get with templates. So I'm gonna put the I operation guarantee back. But if I, wanted to be sneaky in another way, that's why it's called sneaky div. I might say, okay, I'm gonna break my process function a little bit, and I'm gonna say it can only take inputs of float type. Well, now I get a complaint that process does not actually match the interface requirement, so I get enforcement on that side too. So that is that extra type enforcement you get, and the fact that you can get this type enforcement even ahead of compile time is one of the really nice things about generics and interfaces. So by contrast, if you think about GLSL, there's not really a way to accomplish this at all aside from preprocessor defines. And those lack type checking at all. They also lack scope control. So all of your preprocessor defines are ending up getting defined at global scope. So they can inadvertently crash into each other. You can compose them when you didn't mean to. And the code is just harder to read and harder to debug, harder to maintain. So looking down here into the actual body of the compute shader, things might look slightly convoluted because I'm avoiding passing any unresolved generic parameters into the entry point. So I'm using only concrete types. They've been fully defined. The compiler knows exactly how to build a read-write structured buffer of floats. Now, that's not because Slang can't take generic parameters in its entry points, but to have generic parameters in the entry point, you're going to need to do link time specialization. Basically, you need to be able to provide information about what versions of the entry point you actually want to generate for which types at link time. And I don't really have time to dive into that during this session, but there's documentation up on our website if you want to get started with link time specialization. That is a Slang capability. But right now, I'm just going to demonstrate this concept by allowing the dispatching call to pass both a float and an integer version of the buffers. They're going to be separate buffers. And it's going to use this processor choice integer to select what operation it's actually doing at runtime. So looking over here at the Python, then we can see that invoking the shader is actually pretty simple. We start off by just initializing a device. This is where you would provide compiler options. You'd set up your, the same sort of thing you do with a session description in the C runtime compilation API. This is where you would do that, but I am leaving it all at the default for now. And so then loading up our compute shader is just a matter of passing the file name, the name of the module here. And then I also am going to provide the entry point main, compute main, or entry point name of compute main. And then I kick off the compile and get it to return the kernel to me by calling create compute kernel. The next chunk of my file is just creating some buffers for it to operate on. So here I'm using NumPy to create a set of 32 completely random floats, and also using NumPy to instantiate my integer buffer with just the linear sequence from 1 to 32. And then I'll print out all of my buffers before and then after each dispatch, so you can see it being operated on. Looking back at my compute shader, you can see that, the first one, case 0 is going to be just adding 10 to each of the floats. I will then multiply the float by a number, and that number is actually defined up here. It's multiplied by 2, so we'll be multiplying by 2. And then integer, I operate on the integer buffers by first adding 5, and then my next call will be multiplying it by 2 again. So to actually kick off this Python, all I have to do is head over here. Going to see my SlangPy compute example. In this directory, all I have is my main.py and that Slang shader. So I just need to call Python on main.py. All right, so you can see it prints out my initial buffer full of random floats. And then after the first dispatch call, it has added 10 to each of them. After the second dispatch call, it is multiplied each of those by 2. There's my set of integers from 1 to 32. And after the next dispatch, they've had 5 added to them. And then last dispatch just multiplies by 2. So the cool thing about that is that with each dispatch call, it's actually selecting the operation that it does at runtime. I just needed to write that it's all passing through that same generic call to actually invoke the process method. So you can also create individual functions in a Slang module. This was, creating a single compute main entry point and treating it as a full compute shader. But you can create individual functions in a Slang module and let SlangPy generate the entry point itself. SlangPy can also do some pretty clever things, like if you have a Slang function that operates on scalars and you call it from SlangPy with arrays, it can automatically handle the vectorization and marshalling for you behind the scenes. So, it will do the dispatch call and have it operate, on the Slang side, you'll be operating on scalars. But right now, I've just demonstrated the, management of the dispatch myself. Yeah, great. We've written some Slang. We've used Slang concepts like generics and interfaces, but didn't the title of this talk mention Gaussian splats? Yes, now that we have our basics down, we can turn our attention to the Gaussian splats. Before I dive into the code there, I have a lot of windows open. Before I dive into the code, I'm going to just show a couple slides that I showed at Vulcanized this year. So introduced in the 2023 paper, 3D Gaussian splatting for real-time radiance field rendering, Gaussian splats are a simple but powerful means of representing complex 3D scenes using 3D Gaussian distributions as volumetric building blocks. So essentially, a scene gets captured in a series of photographs or videos, and then machine learning methods will closely approximate that scene using those 3D Gaussian volumes. Now, you can get an understanding of exactly how this approach works by operating on a much simpler example in 2D space. So in 2 dimensions, each Gaussian will just instead become a 2D blob, and you no longer need to worry about projecting it into camera space. And then instead of training a set of volumes to approximate a series of pictures, we just train a set of 2D blobs to approximate a single photograph in the same manner. So if each of our blobs is represented as a center point and then a value to express its splattiness, basically big numbers mean it's big, spread out and fuzzy, and small numbers mean it's very focused and narrow, and then a color, then we can generate a big buffer of colorful 2D noise by just filling it with random numbers. And then all we need to do is learn what parameters each of those blobs needs to have in order to make them represent a target image. Now, computing the value of all of the image's pixels from a set of existing Gaussians is easy enough. We just have to go through the list and accumulate all the color values at a particular pixel. This slide here is just pseudocode. I'll show you the real thing in a moment. But the question is, how do we figure out what all of the positions and the colors and the splattinesses need to be? So you can think of this as an optimization problem. If we have a way of expressing mathematically how wrong is this pixel, then we can optimize that function to produce the smallest amount of wrongness. In machine learning, that's called the loss function. So for a set of pixels, calculating the loss function is pretty easy. You just need to know the difference between the color of the pixel produced and the desired target pixel. So here in this pseudocode, we're taking the dot product of that value with itself, which just results in a value that's bigger the wronger that pixel is. And we refer to that as the L2 distance. Now, optimizing that function to produce the smallest possible value involves some differential calculus. And that's what makes Slang exactly the right tool for this job. Slang provides powerful automatic differentiation, which means that instead of having to do a bunch of partial derivatives by hand in your code, you can get Slang to do it for you. So what we essentially want to do is seek the minimum value for that loss. You can see this graphic is kind of doing that for a simple three-dimensional function. And we want to figure out that minimum value by adjusting each of the parameters of all of the Gaussian blobs a little bit at a time until we find that minimum. Now, by taking the partial derivative of the loss function with respect to each of the input parameters, we can determine the gradient of the function, which is just a collection of slopes in relation to each variable, which lets us know how we need to adjust our parameters to move towards that minimum. With Slang able to do that derivative propagation for us, it becomes just a matter of iterating through a process of determining the current loss and then updating all of our parameters to get closer to the minimum. Super simple, right? Just a couple lines. Let's look at the real code. All right, so opening up my simple splatting example. Let's start with the Python. All right, so this handful of pseudocode becomes about 90 lines of Python and 300 of Slang, but most of it is actually either comments or setup code like opening images and allocating space to store stuff. So let's first take a look at the parts of the code that correspond to what we just walked through in our pseudocode. So first is that random set of blobs that makes that 2D big, colorful, bright noise. So that's actually a fairly simple couple of lines of Python right here. All this is doing is using NumPy once again, just like I used it to generate my random floats in the last example. Here, I'm generating a set of 1,800 random floats. That'll be 9 floats per Gaussian blob over 200 blobs. And whereas I represented sigma in the pseudocode as a single float, it's actually a 2x2 covariance matrix, which is 4 floats. I'll show you the math for that in a little bit, but don't worry about it too much right here. We then use a SlangPy tensor to store all of this. What a tensor is basically just like it's similar to a vertex or sorry, a vector or a matrix, except it's got arbitrary dimensionality. And the reason that we're going to use a tensor is that for each of all of these 1,800 random numbers, we're also going to want to store that gradient value, that slope for a partial derivative. The next chunk of code, this is just loading up the image and creating storage where we're going to put that loss value that we calculate. And we also want to store gradient information about that loss because that's the thing that's going to tell us which direction the minimum loss is in. So we create storage for that. It's just empty. And we're setting a starter value of 1 for the derivative values, the gradients. Then we create storage for some inputs to our update function. I'll talk about the update function a little more in just a second. And then like the next part that really corresponds to the code that we showed in pseudocode is the main iteration loop here. And this really is just as simple as it was in the pseudocode. Um, what you see here is that for each loop iteration, we're making two calls into the Slang module. Now, the first call finds the per pixel loss function within the module. And rather than call it directly, what it's doing is invoking the function's backward differential form using that BWDS call. Now, if backward differential sounds a little bit funky, just think of it as a way to estimate the rate of change of a function, that's the gradient, by comparing its current value to what it was just a moment ago. So after this call returns, the per pixel loss tensor is going to contain the current loss value for each pixel and a gradient expressing how that loss value is changing. Is it getting worse or is it getting better? Now, most of the arguments that we're passing to this function should be familiar. This is where we store all of our losses. This blobs is just the current value of all of those floats that represent our Gaussian blobs. And this input image is the image that we're trying to get our blobs to match. Now, this spy grid is a little bit interesting. This is a function provided by SlangPy that lets us automatically generate IDs for each of the invocations of our compute shader that correspond to a shape. So because we're operating on two-dimensional texture, we want to generate IDs that tell each invocation which pixel within the image it's trying to calculate and compare. So we ask SlangPy to generate a grid of ID values in the shape of our image, essentially. Now, the second part of this loop iteration is where we update the parameters of all our blobs based on that gradient information we got. Now, this doesn't actually need to use any differential calculus, so it's just calling the atom update function within the module directly. The atom method is a means of updating the parameters of a model in a way that's more efficient than simply just stepping by a constant amount in the direction of our gradients, but is not critical to understanding how the gradient descent itself works. You could, in fact, just step by constant small amounts if you wanted to. The code for atom update is in the Slang module. I'm going to look at it briefly, but we're not going to dive too deep into it. I do link out to the paper where the atom update method was first introduced. So now we can take a look inside of our Slang functions and see exactly how we go about rendering a Gaussian splat. The function that we called from Python was per pixel loss, or rather the backward differential form of it. So here is that function. And in order for Slang to be able to do the backwards differentiation for that .bwds call to exist, we need to annotate the function as differentiable. Now, one of the cool things about Slang's built-in automatic differentiation support is when you mouse over a call like loss, it will actually call out that it's forward and backward differentiable. This information is embedded into the definition that gets carried around and expressed to you by IntelliSense. So the arguments to per pixel loss here correspond to the ones that we passed from Python. This grad in out tensor is just the Slang side type equivalent to the SlangPy tensor from Python. So output is where we store our per pixel loss values and their gradients. Pixel chord is that grid ID that we generated. We receive it here as a uint pair XY. And then you have your blobs and your texture. Now, in the body of this function, we're passing most of this through to a helper function, loss. All this function really does is take all of those loss values and their gradients and plug them in to the output. So let's take a look at loss. You'll see that this function is also annotated as differentiable, as are all of the function called in this stack. And that's so Slang can generate the derivative of the entire composed function. Now, the body of the loss function here does the evaluation of the blob color at this particular pixel coordinate using simple splat blobs, which once again, differentiable. And then it calculates that L2 loss value exactly as we saw in the pseudocode. The target texture value lookup here, by the way, is marked as not differentiable, because when we're creating the derivative of this big massive function to figure out the gradient of the loss, we don't actually need to track what this pixel value we looked up was at every step of the way. The important part is just this loss that we calculate, and we'll have stored that. Now, the almost last portion of this chain is simple splat blobs. That is right here. So this is the part that looks through our list of blobs and comes up with a color for the current pixel. So as mentioned before, it's differentiable. You can see what it's doing is only slightly more complicated than the pseudocode suggested. It's looping over the entire list of blobs, evaluating each one with this eval call, and then accumulating all of those colors together with a simple alpha blend. Now, there's a little bit of logic that's implemented as part of the Gaussian 2D type to do the evaluation. So let's take a look to see exactly how we get that color in this eval function. All right, so this is where the math shows up. This is why they're called Gaussian splats. As I mentioned, each one of these two-dimensional blobs, or if you're doing 3D Gaussian splatting, the three-dimensional volumes, is a shape and density described by the Gaussian distribution. So the weight of the color value at this distance from the center point is determined by that covariance matrix, which we called sigma. And this is the calculation to determine it in 2 dimensions at least. You can check my math if you want. I've given the link out to Wolfram right here. But that is just how you go about calculating the Gaussian distribution. So with those particular pieces of code, you have everything that you need to do, or that you need to draw Gaussian splats. I have just a couple of caveats for you. Firstly, this thing is slow. So slow, in fact, that rather than run it for you live, I'm going to just show a GIF of it running in a second. Because if I try to run this program and Zoom at the same time, it will definitely hang my graphics card, which is a little bit old. There are a couple of things that I did to simplify this example to demonstrate how gradient descent functions at the core of it, but they make the example run slow. I recently made a post to the Slang developer blog that covers the thing in our original 2D splatting example that it does to be able to run in real time. And I'll include those in my resources slide that I show at the end. And then second, because it's so slow, the example isn't really using enough blobs to get a good resolution on the generated image. You'll remember we only generated enough floats for 200 blobs, but you can still definitely tell what it is. So I will bring up the GIF right here. And that this is our Gaussian blobs learning how to look like a Jeep. This is what you'll get if you actually execute this code. But showing it as a GIF taxes my graphics card a lot less. So there you have it, a little bit of machine learning in action. Now, this same approach and some clever optimization is what drives all of the cool Gaussian splatting demos, the big giant ones you may have seen, as well as some other neural techniques like neural materials. It's really cool, and it all starts with making the compiler do the math for you. So I'll put up my resources slide now. Actually, first I'm going to tell you we have a couple of upcoming events. If you're going to be in Copenhagen at the end of June for high performance graphics, there is going to be a Slang talk there on the Hot 3D track. And then we have a bunch of stuff proposed, but are still waiting for the schedule on SIGGRAPH in Vancouver, mid-August. We've proposed courses, labs, and birds of a feather sessions. So the schedule for that is TBA, but we hope to see you there. And then, yes, here is my resources slide. This QR code will take you to join our Discord. You can join the community and ask questions anytime or show off the cool stuff that you've written with Slang. And with that, I think we are ready to take some questions. All right. Okay, so I think you all can see the questions, but I'll read it out loud as well. And actually, I'll move this off so you can still see all of the links. So is it possible to compile Slang's unresolved generics into C++ templates when using CUDA or a CPU target? I'm going to see Jay or Kai. Do either of you know the answer to that one? I'm not super familiar with CPU targets.
It's not support for now, but we are actually consider to support that because Slang has a plan to support more neural operations in the future. So a lot of neural SDK interact with CUDA. So we are actually has such plan to make Slang interact with CUDA better. So yeah, it's possible, but we just haven't implemented it yet.
All right, and the same attendee also asks, is there a plan to support cooperative vector on a CUDA target? I'm not sure. I'm not sure whether, so I think that's going to depend on whether it exists in CUDA. I don't actually know if it exists in CUDA.
It's not existing in CUDA yet. So as long as CUDA can support it, Slang can support it.
Yeah, so that would depend on whether it gets supported in CUDA, which is sort of outside of the remit of the Slang team. Is it possible to use autodiff for ray tracing with a Vulkan target?
I think we can use all of it, right? I don't quite understand the scope of this question, but in the ray tracing, if you are calling any differentiable function, that function itself can be differentiable, right? So I think it's possible, but I don't understand this question clearly. So
Yeah, I think it might depend on exactly what you're trying to do.
yeah.
The Python package SlangPy seems to be falling behind Slang's main branch. Is it still going to be supported and updated in the future? Absolutely. So SlangPy is under active development. I think fairly recently there was a big merge to it to integrate. It used to have a downstream dependency on another library called SGL. That's now been directly integrated into SlangPy itself. So SlangPy should be expected to take regular updates of Slang itself. And then last one, what are the long-term future plans or roadmap for Slang and its autodiff? That is a very big question. But I know that there's actually a bunch of stuff you can look at. There's proposals up for changes and expansion of the autodiff system. So the best way to get to that probably is if you go to the Slang website, there's a community link, which should link you out, I think, somewhere in there to the proposals. Those can also be found at our GitHub in the spec repository. But yeah, there are active proposals currently open about major updates to autodiff to expand its functionality. I think support for some higher order differentials is one of the things on tap.
Yeah, and also I want to add to this. We are proposing to make the autodiff 2.0, which could extend the autodiff to more object oriented. So yeah, but it's still in the proposing stage.
All right, someone lets us know that our Discord invite looks invalid. That is my bad. I did not actually check that this QR code was still working. So big oops for me. On the Slang website, you should be able to, there's a Discord link at the footer. You should be able to get to our Discord from there.
And I just posted that in the chat there.
Oh, awesome. Thank you so much, Jeff. So ignore this QR code. It's big and taking up lots of the page for no reason. Somebody says it would be incredibly helpful to see an example of a differentiable 3D rasterizer with Slang. They say if they get to writing it, they'll be happy to share, but would appreciate if anybody has the bandwidth to write it. I think that is definitely a call to the community. Most of us on the Slang team have our hands very full just working on the compiler, but we would really love anything that folks can contribute. There's a showcase channel on our Discord, which is the place to show off cool stuff that you have built with Slang. I'm also hoping to showcase some of the cool stuff that the community has done at the Slang Birds of a Feather, if we get that accepted at SIGGRAPH. So if you're going to be at SIGGRAPH, please join the Discord and let me know if there's something really cool that you've built in Slang. All right, somebody says, thank you for this fabulous work. We're really excited about it, so thank you for attending and using it, and please show us the cool stuff that you built with it. A lot of times we just, build a compiler and put it out there and people use it for really cool stuff and we don't know. So please let us know when you build something, because we want to see what you make with Slang. Approximately how much of a performance difference is there between running on Windows with an RTX card versus Apple Silicon? For me, a 4090 versus MacBook M4 Max. Will it be significantly slower? I haven't done any performance comparisons myself. I have been tinkering around with SlangPy on the Mac. The simple splatting example has been the thing that I've been using to try to break stuff, but I haven't run that over on the Mac side yet. So I don't know if I can answer that. Jay or Kai, do either of you have an idea off the top of your head?
No, I haven't done this performance comparison yet.
Yeah, I think I'm a daily driver on Mac, but I haven't really tried to murder the Apple Silicon yet. So I don't have an answer. But if you do start using it on Mac and you notice any major performance differences, file a bug on GitHub and let us know, because that's something that we would want to look into. Does Slang have any plan to support 3JS? Because using Slang to build it to Wigzell, but it can't in using 3 because it's using TSL. I think so. The part of the compiler team that's NVIDIA probably is not going to work on this, but there are community members who are really active on the Slang playground and in Slang or in WebGPU. So this is probably a good thing to bring to the Discord and ask if someone in the community is interested in supporting, because we have there are several contributors to Slang and committers to Slang from outside of NVIDIA, and several of them work very hard on the Slang playground, which I realize I actually have not shown you. So before I go, I just want to make sure that folks here are aware of the Slang playground, where you can actually do live code editing, load up some demos. The full actual runs at real time 2D splatter is available up here on the playground, all running on web GPU. So at any rate, to answer the question, the folks who are doing a lot of the work on the playground may have been investigating 3JS themselves. So I hope that answers things. All right, I think have we managed to get through all the questions? Are there? I've lost my interface, so Jeff, you'll need to tell me.
Oh, yeah. There's one last question.
One last question.
Asking, is there an intersection in capability between Modular's Moho and Max and Slang?
Jay or Kai, do you know anything?
I don't know about the Moho or module. I don't know what's that.
Yeah, I don't know what that is.
Okay. That should be it.
All right. Well, thank you so much, everybody, for attending. I hope you got something useful out of this talk. And please join the Discord. Let us know, what things you want to learn more about, and I can see about putting on another one of these in the future.